Section: Introduction. In this section, we discuss the evolution of large language models, LLMs, over the past few years, highlighting the significant impact of scaling up resources for training. We emphasize the importance of not only efficient training but also inference optimization, since LLMs primarily operate in inference mode post-training. Post-training techniques such as quantization, low-rank adapters, LoRa, and pruning are crucial for reducing the cost and time of fine-tuning and inference. These strategies can be combined to enhance efficiency in resource-constrained environments. Our focus is on a simple pruning strategy for open-weight LLMs, where we identify and remove optimal layers based on their similarity to maintain performance. By leveraging a small amount of fine-tuning after pruning, we can eliminate a substantial fraction of the deepest layers with minimal impact on downstream performance. This approach not only reduces the model's footprint but also provides insights into the network's parameter usage. We observe that deeper layers in LLMs exhibit more similarity to neighboring layers, suggesting a straightforward pruning strategy starting from the penultimate layer. This method, combined with fine-tuning, yields performance comparable to more complex pruning strategies. The effectiveness of layer pruning underscores the potential underutilization of parameters in deeper layers. Key takeaways from our study include the linear decrease in memory footprint and inference time with the number of removed layers, highlighting the power of layer pruning. Additionally, the compatibility of pruning, PEFT, and quantization methods underscores the importance of combining efficiency techniques. Our experiments, conducted on a single A100 GPU, are easily accessible to the open source and academic communities. We further explore the impact of removing deeper layers on model robustness, downstream tasks, and autoregressive loss behavior, suggesting a critical role for shallow layers in storing knowledge. The paper structure includes a literature review, intuition behind our layer pruning strategy, detailed method explanation, experimental results, and future research directions. Additional model, fine-tuning, dataset, and evaluation details can be found in the appendices. Section Summary. In this section, we explore the evolution of large language models, LLMs, and the importance of post-training techniques like quantization, low-rank adapters, LoRa, and pruning to enhance efficiency. By leveraging a combination of these techniques, particularly through a method like QLORA, we demonstrate the ability to remove a significant portion of the deepest layers in models like Llama 2 to 70B with minimal impact on performance. Our findings suggest that deeper layers in LLMs may not be effectively utilized, making layer pruning a powerful tool for reducing memory footprint and inference time while maintaining robust performance. Section: Literature Review. In this section, we explore different methods to make our training process more efficient and discuss some research studies that motivate or provide insights into our approach. We start by looking at the history of pruning and how it is used in modern large language models, LLMs. Pruning involves reducing the size of a trained machine learning model by removing unnecessary parameters, either individually or in groups. Early pruning techniques focused on removing individual parameters based on specific criteria, such as setting very small parameters to 0. Modern researchers have developed various criteria for pruning, especially in computer vision models. Some methods involve iteratively pruning and fine-tuning a network to improve compression ratios and performance. However, simply removing individual parameters can lead to irregular sparsification patterns that are hard to accelerate without specialized hardware. To address this, structured pruning techniques were introduced to remove entire groups of parameters together, like channels or filters in convolutional networks. Researchers have extended structured pruning to computer vision and pre-transformer NLP architectures. Recent work has applied structured pruning to transformers, exploring different components of the model for elimination, such as attention heads, layers, hidden states, and weight matrices. While previous studies mainly focused on BERT-style models for understanding tasks, we concentrate on decoder-only GPT-style models for language generation. There are qualitative differences between BERT and GPT models in terms of layer-wise representation evolution, suggesting that layer-dropping strategies will behave differently for each. Our results show that keeping the last few layers and the very last layer is crucial for effective pruning. Additionally, we found discrepancies with prior studies regarding the similarity between representations in different layers. Our work focuses on large-scale models ranging from 2.7B to 70B parameters, unlike previous studies with smaller models. We also differ in methodology from studies on GPT-style models, where we use a fixed layer dropping strategy after pre-training. Another study on Wave 2 VEC models explored layer pruning based on correlations between layers and downstream metrics, considering encoder-only models mapping speech to embeddings. Their approach included dropping alternate layers, which differs from our focus on decoder-only language models. Section Summary. In this section, we explore various strategies for enhancing post-training efficiency in machine learning models. We delve into the history and modern applications of pruning techniques, contrasting them with distillation methods for reducing parameter counts in large language models. Additionally, we discuss practical approaches for efficient fine-tuning and inference acceleration, alongside investigations into depth-dependent statistical properties of language models that complement our findings. Section: Model distillation. In this section, we explore a different technique called model distillation to reduce the size of a trained machine learning model. This method involves transferring knowledge from a large teacher model to a smaller student model by training the student based on the teacher's predictions. The key idea is to transform the broad knowledge of the teacher into more concise and possibly task-specific representations. In the context of language models, distillation can be done using white box approaches, where the student imitates the teacher's logits or hidden states, or black box approaches, where the student only sees the output tokens generated by the teacher. Compared to layer pruning, distillation methods require more computational resources because they rely on the large teacher model to process a significant amount of data. Our similarity-based pruning strategy, on the other hand, only needs to compute the similarity between representations at different layers on a small subset of data during pre-training. Additionally, our simpler pruning strategy utilizes the reduced model post-pruning. Parameter-efficient fine-tuning, PEFT, is another approach that focuses on reducing the cost of adapting large language models to specific tasks. For example, low-rank adapters, LoRa, help in fine-tuning by introducing a small number of additional trainable weights while keeping the pre-trained model frozen. We use a quantized version called QLORA to make our experiments more cost-effective. Other PEFT methods, such as adjusting the initialization of LoRa matrices to a quantization scheme or choosing LoRa ranks adaptively for different model modules, can be combined with our work for further efficiency gains. To accelerate inference, methods like speculative decoding and Medusa can be used in conjunction with layer-pruned models. Speculative decoding generates tokens quickly from a smaller draft model for parallel evaluation by the main model, while Medusa discards the draft model for extra decoding heads. Combining highly compressed layer-pruned models with speculative decoding could be an interesting approach. Lastly, various studies have explored the depth-dependent properties of language models. These studies investigate how knowledge and linguistic properties are encoded in different layers of the models, shedding light on where information is stored and processed. Understanding these depth-dependent properties can provide insights into model pruning and optimization strategies. Section Summary. Model distillation involves transferring knowledge from a large teacher model to a smaller student model, streamlining and compressing the information. This method can enhance the student's reasoning and instruction following capabilities. Parameter-efficient fine-tuning techniques like low-rank adapters, LoRa, reduce memory and compute costs during specialization to specific tasks, while layer pruning and inference acceleration methods further optimize model efficiency. Studies on depth-dependent properties of language models reveal insights on how knowledge is encoded and processed across different layers, offering valuable insights for model optimization. Section: Intuition. In this section, we will explain our intuition behind layer dropping in neural networks. We think of the representations in each layer as a function that changes gradually as we move through the layers. For a transformer model, the evolution of representations from one layer to the next can be described by an equation that includes the input and parameters for each layer, as well as the transformation function applied in that layer. When we consider removing a layer in a neural network, we need to account for the interconnectedness of the layers. If the network was designed such that each layer's function depended only on the overall input, removing a single layer might not have a significant impact. However, in reality, the layers are not independent. Removing a layer means we have to adjust the input to the subsequent layers to maintain the network's functionality. If the representations in the network stabilize after a few initial layers, meaning they change slowly with respect to the layer index, then removing a layer should only slightly affect the following layers. This suggests that removing shallow layers would have a more significant impact than removing deeper layers. Based on these observations, we have formulated hypotheses that we will test experimentally. 0. We can prune layers in a neural network. 1. Pruning deeper layers should be more successful. 2. Pruned layers should have outputs similar to their inputs. Our main layer pruning algorithm is straightforward. First, we choose the number of layers to prune. Then, we calculate the angular distance between the inputs of the selected layers. Next, we identify the layer where this distance is minimized and proceed to remove a range of layers based on this result. Optionally, we can fine-tune the model to mitigate any discrepancies caused by layer removal. We can measure the angular distance between inputs by considering the inner product of the hidden dimensions of the model. This distance should be small when summed over multiple examples. Fine-tuning after pruning can help maintain performance on specific tasks, but it may not always be necessary depending on the application. In summary, our approach to layer pruning involves analyzing the relationships between layers and adjusting the network accordingly to improve efficiency and performance. Section Summary. In this section, we develop the intuition behind layer dropping in neural networks, focusing on the evolution of representations across layers in a transformer model. By understanding how the representations change with each layer, we can identify which layers are crucial and which can be pruned without significantly affecting the network's performance. Our hypothesis is that by pruning deeper layers that have converged representations and ensuring the input to a pruned layer closely matches its output, we can successfully simplify and optimize the network. Section: Results. In this section, we demonstrate the effectiveness of our pruning strategy on various question-answering benchmarks. We observe a consistent improvement in performance through pruning, especially in larger and deeper models. We also compare our approach with a simpler layer removal strategy. For our experiments, we pruned a range of large language models with different parameters and layers. We used models from the Llama 2, Qwen, Mistral 7B, and Phi 2 families. We fine-tuned these models using a quantization technique called QLORA on a pre-training dataset called Colossal Clean-Crawled Corpus, C4. We evaluated the performance of our models on question-answering benchmarks like Massive Multitask Language Understanding, MMLU, and Boole-Q. We found that pruning a certain fraction of layers led to a sharp drop in accuracy, indicating a critical threshold for model performance. Fine-tuning the pruned models helped maintain performance to some extent. When looking at the loss on next token predictions, we observed that pruning affected the model's ability to predict the next token in the text. However, after fine-tuning, the model showed improved prediction ability, with a gradual increase in loss as more layers were removed. This continuity in performance after fine-tuning contrasts with the sharp transitions seen in question-answering benchmarks, highlighting a disconnect between different evaluation metrics. Section Summary. In this section, we demonstrate the effectiveness of our pruning strategy on various question-answering benchmarks, showcasing a robust transition in performance through layer removal. We observe that autoregressive perplexities of pruned models remain continuous across transition points. By comparing similarity statistics between different layers across model sizes and families, we highlight the effectiveness of our similarity-informed pruning strategy over a simpler remove the deepest layers approach. Section: Angular distances between representations. In this section, we focused on the angular distances between representations in our pruning strategy. We analyzed these distances across 7 models by averaging them over 10,000 samples from the C4 validation set. We referred back to a previous figure that showed the angular distances between different layers within each model. The optimal block to prune for a given size was determined by finding the minimum distance in each row of the heat maps. Across the models, we observed 2 main patterns. Firstly, the smallest distances were found in deeper blocks, indicating that deeper layers are often very similar and can be pruned more easily. Secondly, the distances in the deepest blocks, which include the final layer, were either maximal or close to maximal, suggesting that the final layer should not be pruned. However, there were exceptions to these generalizations, such as in the Phi2-2.7b and Llama 2-7b models. Inspired by these findings, we tested a simpler pruning strategy. This strategy involved removing the deepest block that excludes the final layer when pruning a certain number of layers from a model, followed by a small amount of fine-tuning. This approach, compared to our main similarity-informed pruning strategy, had the advantage of not requiring practitioners to load or infer the unpruned model on a GPU. It also highlighted the importance of optimizing the block to prune. Our experiments showed that the simpler heuristic pruning strategy performed poorly without subsequent healing. However, after healing, the results of the 2 pruning strategies were comparable. This indicated that the purpose of post-pruning fine-tuning is to repair the damage caused by pruning, rather than acquiring additional knowledge. Looking ahead, we reflect on the advancements in making large language models accessible to all, such as the open-weight Llama family. Our work, along with other efficiency tools like LoRa and quantization, allows for significant efficiency gains through a straightforward layer pruning technique. By quantizing to 4-bit precision and applying a layer pruning fraction of 50%, we were able to reduce memory and computational requirements substantially, enabling state-of-the-art models to run efficiently on consumer-level GPUs. As we conclude, we pose several questions for further exploration. What are better layer pruning strategies? How can we improve the healing process? Why does healing eliminate the phase transition in loss but not in QA accuracies? Do different tasks degrade at different depths? Where is knowledge predominantly stored in LLMs? How can we enhance the utilization of parameters in the deepest layers effectively? These questions warrant deeper investigation through comprehensive evaluations and experimentation with various pre-training architectures and objectives.